那你这个 microphone testing。我们直播先开起来测试一下。那麻烦学长待会儿帮我尽量用这支麦，我们会有一支麦方便收音给线上。好，谢谢。我把麦放在这。那个，对。
我等下试一下这边讲话。哎，他的 deckhead 呢？他有一个 deckhead 在上面，怎么不见了？
拿到他说这边这样了。有问题吗？
是还好啦，但是他的 deckhead 不见了，应该在这里吧？看一下。听他这一好。哎，我看到了，在里面。
OK， 难怪。
你那个收音有收到吗？
这好像有，我不知道隔壁教室听没听到。
YouTube 只要有串到就好了。喂。
好，全部开始对外了吗？
对，已经。
到了。一人做，一人做。你刚认识人底吗？我在平时在出去的，人家是临时科，然后contributor。你做这么小点，我交回去的。没有，没有，没差。好厉害！哦，聊干嘛？也不要挖脚。对吧？都来看，你要大哥吗？还是你听到别人？我待会跟你讲，我就是来看。OK， 好，看啊，哦。你们两个坐两边旁边这个，你这个讲，这个。那先没听错，还是我离你不坐两边哪个地方？因为旁边是一个就是这样子，坐了，因为其他是一个，你们录影是什么时候控制的？就是说现在其实他在录吗 ？OK， 所以我偷一点时间，你介意吗？还是还好？OK。1, 2, 3, 1, 2, 3. Microsoft speak. Okay, so actually we are fully packed with our schedule today, so I will be presenting more earlier. And so if it's okay, then please sit down to have a seat, and I will start my session right now. So this is the command. Please remember that this is the magic happens. So allow me to introduce myself. Wait a minute. Okay, good evening, ladies and gents. Welcome to the World RISC-V Day at Hsinchu. And today I will be presenting the warm-up talk RISC-V, the open standard, the open implementation, and open silicon. So who am I? My name is Runlen, and I currently work for Andis Technology. And I currently humbly serving as the chair of the System Library Working Group in the RISE project, which means the RISC-V software ecosystem. And my expertise basically for the operating system and some system libraries. So everyone's talking about RISC-V is open, open, and open. So what exactly is open? RISC-V itself is an open standard. Anything ratified in RISC-V standard is either patent-free or transferred to the RISC-V International. So if a student wants to implement the RISC-V standard compliant core, it is free. But it is a very common misunderstanding that everything is open source. It's not. For example, that Andis has donated our pack SIMD instruction to become the P extension, but Andis is not donating our RTL code or our microarchitecture design. So this is very widely misunderstood. And so people will ask why open standard is important. Well, because the closed ISA company will come after you, and they do. Here is a news piece from the EE Times saying that a student tried to implement ARM's V7 instruction set, and somehow it doesn't go well. So this is what happens when you're using the non-open source or non-open standard. And so before the RISC-V, that people try, especially people from academia, try to propose an open implementation called OpenRISC. And actually, some IC vendors, such as Owinner, adopts it to become the coprocessor in some of their SoCs. But that doesn't go well as well. Doesn't go well either, sorry. The problem is very sad but simple. IC company doesn't like to adopt GPL code inside their designs. So, and the other issue is that DLX ISA is too steampunk in the modern era. So, people from the academia came up with a different idea. It's called open standard, and it's like a trickle down method. If people familiar with economics, there is a term called trickle down economics that means the wealth will come from the top to the down, and somehow it is proven to be wrong. But for the software ecosystem or hardware ecosystem is actually working. C language is an open standard. We have MSVC, GCC, and CLAN. Unix and POSIX are open standards. We have Solaris and Linux right now. Hence, RISC-V is an open standard, allowing people to contribute and adopt it differently. And proprietary software hardware companies can make fortune out of it, such as just like Andis have done it. But the open software and the hardware could accomplish the things undone or the things have been done poorly. So the funding will trickle down from the standard to the implementations. And even though everything is free, but we still need a barrel hoop to keep everything on track. So RISC-V International is basically the governing organization for RISC-V to evolve without going too wild. And this is very proudly to become one of the founding members. And this is our founding CEO and the CTO, Frank Welling and Dr. Charlie Su. So we're talking about different level of openness. We have open standard and closed source implementation. In the back, we have our Android on the Kili demo, which is our SoC. It follows the open standard, but implemented with the closed source. And some people will say, hey, I want something open instead of something closed down. So there are open source implementations. There are many open soft cores running on FPGA, such as this one. This is an ECP5 FPGA board supported by the FOSS, the free and open source EDA toolchains. And if you want, actually, it is possible to do it with the real silicon. You can tape out your silicons with under €700 today, and it runs Linux. And so let's ask ourselves why open standard is important. Common interest means common code. The software ecosystem is too big a task for a single company to handle. Has Linaro gathered the engineer of working for us to flourish their software ecosystem, and likewise, RISC-V established an equivalent to help the software to adapt. If you're familiar with manga or anime, you know this alien chimpanzee posing this poster, say 人气蛋. So it's basically like the same thing in the RISC-V software ecosystem. We are gathering the 元气, the Genki from everyone. Like the Bible say that I can achieve all things by the power given to me. So public money means public code, and this is also very proud to be one of the founding member of RISC. So what do we do? What have we done in RISC? That in System Library Working Group I'm in charge of, we have done many things in the codecs and runtimes. For instance, the late JPEG Turbo, we have collaborated with it within providing vector optimizations, and the embedded TLS, we also have the scalar crypto optimization. And for QEMU, some people here are from my previous employer, Sci-Fi, is actually contributing a lot in the QEMU for the vector emulation, and this will also contribute a lot in the LPMP support. So it's an open source and an open group for everyone to contribute. Even though we are competitors, still we are working the same arena to do things. So enough of business talk. I'm sorry, this is supposed to be engineer talk, so I promise that's all the business talk, and from here is for engineer talk. And people will ask, how can I mess with RISC-V without getting Mr. Piggy, without breaking your piggy bank? For close design, here is an $8, so this is the $8 BL AOA is used by the board called ARC64, which is only $8, and it runs Linux on it. And if you want open source design, just like I said, you have the ECP5 board, or this one, the LaQuiz computer, which is Germany based, and it runs Linux with a very old style GUI on it. It costs like €100. And for the software ecosystem, if you're buying the closed source one, well, you just simply ask the vendor because they sell you things. They sell you things they're supposed to provide the customer service. If they don't service you well, maybe buy some products from this. Anyways, so for the open source design, my personal 2 cents are it's your best choice to use the open source FPGA torsion targeting the open source boards, because it's just like I repeatedly say that if you're using the public code, it is a common interest, and people will help you if you're polite and you have done your homework. And here are the projects that you can take a look if you're interested in them. And if you're only doing the software part, I would suggest just use broot plus the QEMU user static. My past experience on porting the Alpine Linux on it is basically done on these 2 projects. And let me jump through a little bit. So people will say, okay, I just want to know which projects I can use. This is the one that I would think is the best part. It is called LightX versus Phi. LightX itself is an open source SOC generator, which means that it can generate SOC design with UART, SPI, stuff like that, along with the CPU core. And the most widely adopted core, there is a VexRISC-V, which is capable. So people will say, enough talk about this high level thing. Remember the comment I showed you in the beginning of this talk? Actually, that is here. So this means that I have already synthesized place and route and bit generate a CPU core during this 20 minutes or something, and it's right here. Well, the timestamp is a little bit wrong, but it's just trust me, it's generated right there because the NTP is a little bit wrong on my computer, so it's just generated right now. Anyways, so you basically see the demo that you can do it with just 20 minutes and something. You can install the Linux framework and to generate the bitstring with the proper factory SPI SMP variant and with the Linux capable privilege mode toggled and SPI for the SD card and for the frame buffer. So this is the thing you can do. But people will never satisfy with something is running on FPGA, saying that it is fake. It is something that reside in the lookup tables. They are not real silicon. So before 2020, this is a pipe dream, and after 2020, this is a reality. Tiny tape-out and MPW service targeting the Skywater 130 nanometer process node using the only free and open source EDA and PDK could let you do this tiny chip running Linux on it. And here is the shell. It's running very slow, like only 30 megahertz, but it's open source, completely down to the transistor, to the metal, and get the mask and tape out to the silicon right here. People before 2020 say that this is completely impossible, but it is now. It is running right from here in the podium. So to do this, you need a different EDA toolchain with the OpenLAM, and it targets the only two open source PDK right now. And if you're interested in, you can go through their guides and tape out yourself. And I think that's all today. And I just want to give you this outro. The GCC 1.0 was released like 30 years ago, and nobody really give a care about it. But now nobody doubts that GCC is something important. Unix standard was released in 1994, and Finnish student was unhappy to pay for a copy of Unix, actually Minix, and wrote himself a Unix-like system. The internet regarded it as a toy. Actually, there is a professor, Tenenbaum, saying that this is a toy and is designed very awfully. But today, 90% of the servers are running GNU Linux. Intel 404 was releasing like 40 years ago. But in 2020 and in 11, the resounding spec appeared. RISC-V will set your CPU free. And that's all. Thank you. Flo, I think it's your turn. 这个你要怎么查？不好意思。
去开会议
都可以，对，
谢谢。Thank you。
你可以帮我的 slide 吗 ？No, this one.
Okay. You can use this.
Okay, perfect. 没关系，OK 了。Okay, good evening, everyone. My name is Flo. I'm from the Open Hardware Foundation. We just heard about RISC-V, how it sets free your instruction set. Ruinland was giving us some really great examples how we can use it. And I want to give you some overview about the Open Hardware Group and how we are also helping to bring more open source RISC-V to the world. So 3 points I want to talk today. The first one is the industrial grade and open source course. What can you do with it? So I would like to show you that there are real applications outside in the wild where you can use RISC-V. Then I would like to show you what the roadmap is we have here at Open Hardware and a few cores. And last but not least, I also want to give some incentives why you should or could join the Open Hardware group. Okay, let's start with some case study. This pointer is not working, so I keep standing here, apologize. First, why to have open source RISC-V? First, you have unlimited flexibility. You can use the core, you can modify, you can add your custom instructions. So it makes things much more easier, no matter if you're going for some off-the-shelf product or for some customized project. Here in the university, especially for research and academia, you have the big advantage with some open source RISC-V is that you can use designs which are used in real world. So you can do your research, you can see how to improve it, or you just can use it for studying based on what other people, what other companies have put into real productions. And then here at the Open Hardware Group, we are ranging from deeply embedded over microcontroller level up to application-ready cores. So application-ready cores, that's something where you, for example, can run Linux. But let's start with the microcontroller. In our GitHub repository, which is open available, so you can go there, you can download all of the code. We have, for example, this microcontroller system. You have Open Hardware Core, that is the white one here on the right side. You have some other IP inside and also some IOs. This design actually we have taped out in Global Foundries 22 nanometer FDX process. So it's a proven design, it is tested. There is actually some university in Canada, University of Saskatchewan. They have taken our sample design and they have modified the PDK to make it radiation hardening, so to put it in space. That's just one of the examples you can do if you have a fully open source system. But here this whole system is open source, so you can download it, you can put it on an FPGA, or if you have a product, you also could make an ASIC from it. If we are going a little bit further, the University ETH in Zurich, Switzerland, they have made a chip. They actually have put a, they call it end-to-end open source 64-bit Linux system. So what they did, they used open PDKs, they used open source software like OpenRoad, Yosys, and other software to synthesize this core. They have our open hardware CVA6 Linux ready core inside. They have a DMA, USB, VGA, and all of this IP is fully open source. So you can go there, you can download it, you can tape out your own chip, you can study it, you can modify it. And actually, if you're taking a picture of this QR code, it will bring you right to the website so you can download the white paper, the PDF, and give it a read what they have done. It's quite amazing. And especially for a university to get all of this IP, to be able to freely tape out in an advanced node, I think that is really a great achievement. And you also can see 2.7 million gates used in this, always open source. I think in hardware, we are really in for a revolution for making ASICs or chips. So that could be a good starting point. Then some more in the industrial side. There is a company called Accelera AI. They are in Europe. They are making this compute in memory accelerator, edge accelerator. They are using multiple RISC-V cores inside. So they have Andes technology, but they also have other solutions inside. Then we have automotive, German company Bosch. They are putting this RISC-V in an ADAS, in an auto, for an object detection. So they had an existing system with ARM. They have taken out the ARM and replaced it with the open hardware CVA6. These test chips are now back from manufacturing and they are using it internally for doing some evaluation and also checking on the software. That's all possible if you have a fully open source design. So you can not only use it in research, you also can use it when you're finding your startup, or if you're a super huge company, you also can implement it for quick testing or other things. Another company, also a European company called Infineon, they are also making a lot of chips for automotive, and they are also committing to put more RISC-V inside. Why I'm putting these things here, because I think that is also a clear sign that RISC-V is the future. if you're studying this now and you will come on the market, you should be easy possible to find jobs with RISC-V knowledge. Okay, then what are the motivations to join, for example, Open Hardware Group and how we are working? Maybe some of the examples that you can collaborate with other universities. For example, we have universities from France, from Canada, United States, Israel. They all come together, they work together, they share work. One want to research a branch predictor, others want to work on some cache coherence protocols. So they all come together, everyone does some of the work, they find other partners to tape out. Collaboration is really a very powerful point. Also, access to cutting edge RISC-V hardware is another point. And definitely working inside the open hardware, bringing your own ideas. You're also shaping the direction. So you can bring your input, what should be the next feature we are adding. Plus, you're recognized. If you're collaborating, it's a fully open source project. So you can go to a future employer and say, look, I already worked in RISC-V. I supported the open hardware. Here's my GitHub. You can see what I have contributed, just as an idea for students. Then there are also different members. To be honest, that's a little bit boring. They all love us, of course. They all use our products, but I'm not going to read this. So maybe we have the slides later available. Silicon Labs is using this RISC-V already in production. So there are Wi-Fi or maybe Bluetooth controller, which have open hardware inside. Tal is a big European company. They are also shipping, for example, CBA6, which I have seen already before. All right, more interesting. Where do I find the course? Or better, what are we delivering? So the core itself, written in system Verilog or Verilog, it's Apache 2.0 license. That means you can take it, you can modify it, you can make a commercial product. You don't need to tell us if you don't want. Of course, you're always welcome to contribute back, but the core itself fully available. Then verification, the verification framework is also fully available. Actually, verification is very underrated because to make a RISC-V core is very easy, but to verify it, to make sure there is no bug inside, that's where companies spend a lot of money. So verification is super important, but also the overlying software compilers like Ruinland mentioned, GCC, but also emulators like QEMU, all these things to develop software in an early stage and to have it ready is really important to have all together so you have a head start and can really quickly deploy. Then also documentation, also freely available by the way from us. And last but not least, some implementations for FPGAs, but also for SoCs like in the example before. From a roadmap, we are ranging from very low power over microcontroller style up to the application cores. I just quickly want to put 3 of the cores on site. This one, the CV32E40P, is industrial grade core, so you can take it. It's fully verified. It's implementing a P extension, also not the ratified P extension. It's kind of a custom version, unfortunately. But Charlie, I hope we can change this. There are also other things inside. So this core is already in mass production. In other words, if you're looking for a core microcontroller type ready where you want to research or innovate or make a product, you can grab this core from our GitHub and thanks to Apache license, just deploy it in a commercial product or in a research. The CV Wally or CVW is a core which is developed by the Harvey Mudd College in America. Los Angeles is this. What they are actually doing is really cool. It's a 5-stage core. They are having a Linux-capable core. They are currently working on implementing the vector. They are implementing a fully verification. Verification will be also industrial grade by summer of next year. really interesting because this textbook you see here, that is describing the decisions, the design decisions for building up the core. And there will be a new book out by end of this year, which also goes more into the detail how to make a complete SoC. That means taking the core, the CD Volley core, adding it with verification and other things. Quite a lot of universities are teaching based on this. I was joining Andes Technology in 2019, I think, and that was also one of the books I got recommended. So I was reading this, had a lot of details about the internal workings of a microarchitecture. So I personally just can highly recommend this. Then the CBA6 is the last core I wanted to quickly touch. Ruinland also has touched it before. That is really a nice core, fully open source. There are a lot of academic usages, not only from ETH Zurich. I was recently in Japan. There I saw a use case. Siemens is using it for some demonstration towards customer about floating point unit and things like this. There are different models available from this core, like 32-bit or 64-bit. Also quite interesting, especially when you want to run Linux. In the RISC-V summit in Europe, I was able to see a demo on this, running, of course, Doom, but I also could actually play Tetris. I have to say Tetris was quite more entertaining for me. But this core is already working, so if you want to do research or, again, a product, you could grab this and start working with it. All right, how to work with the Open Hardware Group. So we're an open source group, but we are also somehow organized. We have this kind of technical working group, which is the top level, and then we have different subgroups where we are discussing about microarchitecture, verification, software, or also safety and security tasks. So there are a lot of different things we are having working in parallel. No matter if you're more on the design side, on the verification, or even on the software side, there's definitely a place for you where you could have a look in the Open Hardware Foundation and maybe even join us and collaborate with us. We're an open source foundation. However, there are also member fees. I got quite a lot of questions for it. So the good news is the member fees are mainly for commercial companies who want to join us. You still can take it. You don't need to join it. Member fees are relatively small. So a lot of companies join us as a kind of appreciation because they want to support us, the work we are doing. For universities, it's really good. For universities, it's free of charge. So a university can join as a guest member. You can interact with all the other universities in open hardware, with commercial companies. For example, we have some French companies working with universities, sponsoring students to work on certain things or do research on it. So have a look, join us, contact me if you like. By the way, I'm personally located here in Hsinchu, so if you have some questions, always welcome to contact. And why do work with us? I think that's already what we said before, that you have more openness, that you have more the right to modify, to implement as you want, but also more transparency. What is happening? Why are things changing? Remember, we are completely open, so everything is on GitHub. You can check each different change happen on the core. And currently, I think there is not so many hardware. For software, everything is open source. We are kind of used to it. For hardware, that is now starting. Here in Open Hardware Group, we are one of the biggest groups doing this, and I invite you to join us. Open Hardware itself belongs to the Eclipse Foundation. So here in the Eclipse Foundation, we are doing the cores, tool chains, also a little bit operating systems. And then inside the Eclipse Foundation, we also would have other things like IDEs. We have a safety critical, safety certified real-time operating system, ThreadX. There is an IoT initiative, and there is also some various automotive initiatives. So just more interest to join us as a group, because there are also other things to get cool projects and to collaborate with others. All right. So thanks for your attention. I will be around here. If you have any questions, feel free to check with me and I would be happy to answer your questions. Thank you.
We have around 4 minutes before the next meeting. So any Q&As?
See, you told me to be on time and I be on time.
Yeah, you're on time.
You can hold the microphone. Okay.
That was okay, then就问你的话，就是你可以到。怎么要怎么来说？ Question, if I can ask.
Sure, please.
I'm just being asked to phrase this. So, obviously, if you're a commodity company, it's great. I think you touched on this in your talk. It's great if there's like a open source RTL that I can use for my chip because that saves me a lot of work. But the reason a lot of companies at the moment might still not want to use OpenRTL on the internet, or whether they choose to use, I guess, what's a competitor in like ARM's CPU IPs, because obviously ARM will then guarantee that this CPU is free of any bugs whatsoever. They can guarantee it, and I don't have to spend as a company engineering effort on verifying this thing. What is your thoughts on how this is like the source idea? Because you mentioned that you're doing some stuff with UV test benches or whatever. What's your vision of how that part can be developed or RISC-V to make it easier for people to do the verification of the IP as well? So I'm saying, is that part of something you can sort of do?
Excellent question. So let me see how I can answer this best. I think in the RISC-V ecosystem, the main thing which we have is the specification, which is fully open. The implementation don't has to be necessarily fully open. Ours, for example, is fully open, but you mentioned a very critical point. If people license a core from ARM, they get fully support, they get the assurance there are no bugs inside, they have a very comprehensive set. If people come to open hardware, we are not offering this. We cannot offer this. We are open source. We are living on work by volunteers. However, in the RISC-V ecosystem, you have companies like Endis Technology, and they are doing exactly this. So if you go to Endis, they offer you the RISC-V core. There is everything comprehensive. There are great tool chains. There are fully support, great documentation, plus the assurance that there are no bugs inside. So that means in the end, it comes really down to the company if they want to go to someone like ARM, which maybe still is a way, but not the future for sure. So most likely in the future, they will decide, should I go to Endis Technology or should I go to open source like Open Hardware? And here I personally believe that it will be a good mix because, for example, high-end cores are very complex. So Endis Technology has a lot of experience. They have really great cores. If you license this, you know everything is verified, everything is working. And then on the other hand, open hardware for some smaller cores or something like this, that's where I think it can fully put inside. But in the end, it really comes down to the risk profile or the how many risk the company is willing to take who is designing the chip. For example, if you're talking with some European companies, they look at open hardware, they maybe test something, but they never ever will implement it in a product. They will license from Endis Technology because they want the assurance, they want to be able to talk with some engineers to get the support. That's nothing we can do in open source. But some startups who are making, for example, an AI accelerator or some cool sensors or maybe even a Linux-capable system, they have a different point of view. They look on it and say, that's not a mission-critical thing, and we just test it, and if it works for our application, we go with open source. So it really comes down a lot to the companies and how that will develop in future. To the last part of your question, In open hardware, we have very extensive verification. So we are measuring the quality in TRL levels. That's from the NASA technical readiness level. If you make a product in a university and you make a test chip, normally you have TRL3. Works, maybe needs some patches, but okay. If you want to go into industrial production, you need to have TRL5. That means every detail fully verified, everything tested, no dead code inside. You know exactly everything. That's what Endis technology has, but that's also what we have for some products, not for all, because it's really a lot of work. So some of our products have this, and we are working currently to add labels to the products to give you the quality level what you have so you can check it. But yeah, so I think open hardware will come. We will have verification, but I also believe we always will have commercial vendors in RISC-V and open source vendors, because if you're going fast, if you're a big company or maybe even a small, it really can make a lot of sense to have a strong partner with a lot of people who can help you, who can give you support. In open source, you need to do most of it by yourself. It's not necessarily bad, but if you're on a deadline. All right, thank you very much.
帮我们再来选前这个好，谢谢，这个麻烦。OK，
谢谢
不。会的。
然后，
这
好，就好，大家晚安。然后我今天很感谢Rinland 学长邀请，然后有机会来跟大家分享U-boot for RISC-V lifting off your RISC-V system 的这个分享，这样，对，然后这个活动是想要让大家就是多接触 RISC-V 相关的东西嘛。那如果想要接触 RISC-V 相关的东西，不外乎就是读文件啊，然后可能自己动手做，对吗？那我们今天就来看一些小文件，然后跟看后面有一些步骤，大家可以照着做，然后可以跑一个 RISC-V 的 U-boot 起来，这样，然后先跟大家自我介绍一下，我是梁玉琪，然后也是交大毕业的，然后可以叫我 Leo 就好。然后我目前现职也是金星科技，然后在软体处的 Linux 组这样。然后我们 Linux 组主要的业务会包含提供客户一些 BSP 相关的东西，所以里面也会包含 bootloader。然后 U-boot 就是在我们 BSP 里面的 bootloader， 然后我们目前也是U-boot RISC-V 的 maintainer 这样。然后我 email 在这边，如果大家有什么技术交流想要技术的相关东西想要跟我交流，或职涯相关的问题都可以寄信给我这样。嘿，对，就是这个是一个就是想说大家如果有问题可以，本来刚才是想要说，就是大家有问题最后面可以问这样，然后可以问为什么要戴口罩这样。然后其实是因为没有刮胡子。好，那我们继续。然后这次的分享会希望让大家可以更了解 RISC-V 相关的东西，然后RISC-V ISA 相关的东西，然后如果可以的话，可以在 RISC-V 相关的系统上跑起来，然后并了解它跑起来是怎样的行为。然后后面有一些流程可以让大家跟着一步骤的做，然后可以跑起来一个 U-boot 的环境在 QEMU 上面，就是刚才Rinland 学长有提到的 QEMU 上面，然后用 Build 来编的，大概会是这样的流程。那所以我们的 outline 会有先跟大家简单的介绍一下 RISC-V 这个 Open Standard， 然后再来跟大家分享一下 Common 的 boot flow 大概会长怎样。然后在 RISC-V booting 的过程啊，就会用到 U-boot 的这个软体专案跟还有 OpenSBI 这个软体专案，那等一下也会跟大家分享一下。 然后最后会一步一步的来看那个整个开机的过程做了哪些事情，然后最后再跟大家分享一些U 部里面可以大家有兴趣可以在研究的地方这样，然后最后是 reference 的部分这样。这么好。那刚才那个 Rinan 学长还有那个 Florian 都有提到 RISC-V 相关的事情。那我这边的理解上，就是 RISC-V 是一个 ISA， 然后ISA 它想要定义的就是软体跟硬体之间的界面。那就是 ISA 它会定可能我们这个 ISA 里面会有哪些指令，或者是 memory 相关 addressing 的 mode， 然后它可能会有哪些 register。然后还有这个 ISA 它有的 privilege level 跟 memory model， 那这样就是hardware要照这些 instruction 的描述来实作，然后这样 software 就可以预期这条指令它会带来的行为是什么，然后还有hardware 可能就是要实作，不好意思，谢谢。感谢。然后就是 hardware 可能要实做一些这个 ISA 里面有定义的一些 register， 然后这样让 software 知道我有哪些 register 可以用，类似这样的行为这样。然后在 RISC-V 里面，我们可以看到等一下，就是这张图啊，这边是在说 RISC-V 里面它的 privilege level 是有哪些，然后有分virtualized 跟 non-virtualized 的这样，然后在右边这边就是说 RISC-V 它的 page table 的长相是怎样。那这边要提这个的意思是说，在 RISC-V 里面的 page table worker 会是硬体做的，然后软体就可以根据这个 ISA 所定的东西，在相对应的东西相对应的位置填好它所需要的资料之后，硬体就可以照这个格式来解读。所以就是 ISA 就是要定义好software 跟 hardware 之间的那个界面这样。然后 RISC-V 它这边的特点会是，也是刚才 Florian 跟 Rinan 都有提到的，它是 royalty free 的，然后它是 open standard 跟它是 modularized 的。然后royalty free 跟 open standard 的话，它这样就是代表大家的进入门槛都比较低，所以如果像 startups 或者是一些研究机构想要来做研究的话，就可以比较没有门槛的来做这件事情，没有成本的来做这件事情这样。然后另外 modularity 的部分是说RISC-V 相关的 extension 都是可以大部分的会有一个 base 的 extension， 但大部分后续新加的 extension 都是可以选择要不要实做的这样。然后所以它的可以选择的话，就代表会有很多多样性这样，然后你可以针对你的应用来做选择这样。那这个是这个 ISA 的部分，然后所以大概这边可以大概有印象的是RISC-V 这边有分 M-mode、S-mode 跟 U-mode， 然后它的 page table 大概是长这样，然后它是一个 open 的ISA。好，然后接下来跟大家分享一下，通常一个机器开机的话，它会有哪些流程这样。那通常会有这个5个步骤，会是一开始的 ROM code， 然后把第一阶段的 loader 带起来，然后那个 loader 会再去把接下来的 runtime 还有 bootloader 再放到 memory 上来执行，最后再去找它最后要 boot 的 OS 大概会是在哪里这样。那通常一开始的 ROM code 是放在一个非挥发性的储存装置上面，所以每次断电的时候，它都还会存在在非挥发性的机体储存装置上面这样。然后通常是 platform dependent 的，然后接下来它会把下一阶段的 loader load 起来，然后再 jump 过去。然后在这边的话，通常会 load 的是像是 BIOS UEFI 这种，或者是我们等一下会提到的 U 部 SPO。然后接下来它会再把后续的 runtime 跟后续的 bootloader 再 load 上来，所以这个 loader 它想要做的事情是 load 接下来的软体，然后后续的 bootloader 才会是去 load 真正的 OS 这样。然后这里的 runtime 会像是 ARM 里面的 ATF、ARM Trusted Firmware， 或者是像 RISC-V 里面的 OpenSBI。 然后再来的 bootloader 这个部分就是要来 load 后续的 OS， 然后它可能会需要比较丰富的能力，比如说它可以从网络开机，或者是它可以拿 MMC 上的东西等等的，所以它的 code size 也会比较大，所以我们的 code size 大概会是往这里涨的，然后最后才是 boot 一个 OS 起来这样。哦，对，顺便提一下，如果大家有任何问题想要问的话，都可以随时打断我这样。
我有个问题哦，
好，
可能对软体部分算是门外汉，可是这个runtime services 的那段是吗？是用来做什么？
好，那后面会有比较深入的分享，但这边的话可以简单回答，就是它会是有点像是应该说它可以有点像是 kernel 要存取一些硬体的资源的时候用的一些 runtime services， 这样就有点像 user space call system call， 那它会进到 kernel， 那 kernel 要存取一些 runtime 的硬体的资源的话，它会就是用这个 runtime 来存取硬体资源等等等。
你想要拿16台电，会打一个 RD cycle 下来，可是它其实是一个 pseudo instruction。我主要针对OpenSBI 的那个，比如说你在 CPU 当中想要拿的，那你现在把类似的 instructions， 可是 RISC-V 它想要把这种一个 instruction 就发展到 pseudo instruction， 但是它是 override， 那其实它会打到 OpenSBI 来之后，这就是它的方式。还有一些 RISC-V design 上它是用非抽象化的东西放在这里，对，还有双位合作。
感谢 Ryan 的补充，没错，大概是这样。好，那我们这边举一点比较实际的例子，就像如果 ARM 世界的话，它会是一个 ROM code， 接下来进到 UBOO SPL 或者是 ARM Trusted Firmware 的 BL2， 然后接下来再进到那个把它的 ATF BL31 load 进来，它是那个 ARM Trusted Firmware 里面的 Secure Monitor 这样，然后也把 UBOO Proper load 进来。然后再跳过去执行，然后最后从 UBOO Proper 再去找要的 OS。那在 RISC-V 世界里面的话，就会是像下面的图一样，会有一开始的 ROM code， 然后进到 UBOO SPL， 然后 UBOO SPL 会把 OpenSBI 跟 UBOO Proper， 等一下也会跟大家比较详细的分享他们两个做了什么事情这样。然后就是把这两段的软体 load 到 memory 上，然后再去执行，最后从 UBOO Proper 找到 OS 来 boot 这样。然后刚才有提到 UBOO 跟 OpenSBI 嘛，那 UBOO 就是一个很常见的 bootloader， 它代指的是叫 Universal Bootloader 这样，因为它大概支援1000多种板子的开机，有横跨各个架构，然后它最主要有的目的会是两个，一个是做 bootloader 用，然后一个是做很前期的 hardware debugger 用的。然后 bootloader 的部分就是对。常见于嵌入式的装置，然后很常需要 DTS 的支援，这样来知道硬体有哪些资源这样。然后 hardware debugger 的部分是因为UBOO 它本身是支援很多的 device driver 的，然后它也有一个 interactive 的 shell 可以使用，所以它可以用一些指令来测试很前期开发的时候的 hardware 这样。然后 OpenSBI 的话，这边是 RISC-V 世界里面的一个 firmware， 它叫 SBI Spec。RISC-V 里面有一个 SBI Spec， 它是 Supervisor Binary Interface 的简称。那可以想象刚才提到有 MMO 最底层的 MMO， 然后 SMO 跟 UMO， 这边可以把它跟 X-Bio 的想象起来是有点像 X-Bio 的 Ring 0、Ring 1、Ring 2、Ring 3这样，或者是 ARM 世界的是 Exception Level 的1、2、3，类似这样的概念。然后它这边就是想要划分那个权限的阶级，让最高权限的可以存取最低权限的不能存取高权限的资源这样。然后 SBI 的话就是介在 MMO 跟 SMO 之间的 interface， 就是 SMO 如果需要存取 MMO 资源的话，它不能直接去存取。在这边具体来说的话，可能是像 RISC-V 世界里面会定 MMO 有一些 register 是在 MMO 才可以存取的。那 SMO 想要存取那些 register 的话，它就要透过这个 SBI 的 interface。然后 OpenSBI 的话，它是 SBI 的一个实作 ，SBI 是一个规范，然后 OpenSBI 是它的一个软体实作，这样。 所以这边是一个 U 部跟 OpenSBI 的部分。那我们接下来就是来一点点静态的实作，这样就是这边有 build root 的部分，刚才 Rinland 学长也有提到，就 build root 可以来编很多有趣的东西，然后这边是其中一个部分，我们可以用来编 U-boot， 然后等一下可以在那个 QEMU 的模拟环境上跑起来，就是如果大家想要尝试的话，可以从这边来入门这样，然后这边如果一开始直接使用 build root 的话，它会不包含U-boot 的部分，所以我们可能要多做这些事情。先 clone 下来之后，进到那个 build root 的资料夹里面，然后我们用 QEMU 的这个模拟环境来实做这样，然后里面把 U-boot 选起来，然后选最接近的release version 这样。然后接下来把这边相关的东西都勾起来之后，再打 make， 你就可以编出右边这边的东西。然后右边这边东西就是待会等一下我们会拿来 boot 的一些 binary 这样。然后如果是没有选 U-boot 的话，直接执行这个 start QEMU 就也可以把 QEMU 带起来。那它这边带起来的是 QEMU， 然后直接用 OpenSBI 当做 loader 的状况这样。好，那如果我们刚才编好的东西，接下来我们用 QEMU 的 boot command 来做。那这边跟大家简单分享一下这个 boot command 做了什么事情。然后 QEMU 就是用 RISC-V 的 QEMU， 然后这是 System Mode， 所以它可以模拟一个 RISC-V 的系统。然后减 SMP4 的话，就是代表它有4个核心；减 M1G 就是它有1G 的 RAM。然后减 Machine Virt 就是代表它是一个 virtual 的板子，它没有模拟目前市面上有的板子。那目前在 QEMU 的 repo 里面，市面上的板子也有像 Sci-Fi 的、像 Andis 的板子都有这样。那就可以到时候如果大家有兴趣，可以再去看它的 document 这样。然后这边减 BIOS 的部分就是把 OpenSBI 放到这个位置来。然后 QEMU 它本身就有一个 ROM code 了，所以目前做到的事情就是这里 ROM code 摆好，然后把 OpenSBI 摆上去这样。然后再来是减 device loader 这个 file 是把这一个档案 uboot.itb 放在0x802550的位置。那这个 uboot.itb 等一下它所包含的东西是这个 OpenSBI 跟 uboot proper 2个东西绑在一起，这是 uboot 里面比较特别的方式，它会把它绑在一起，然后先放到 memory 的某个位置，然后 uboot.SPL 会再去那个 memory 的位置拿这2个东西把它解出来，然后再放到它们相对应该要执行的位置这样，然后最后就可以再把想要 boot 的kernel image 丢上去，然后就可以 boot 到 OS 里面。然后这边有列一个，这个是之后如果会 boot 到这个就是它的那个 hard disk， 然后里面有的东西是那个它 root file system 的。那如果照刚才的指令执行的话，大概会有这样的 output。前面是 uboot.SPL 的部分，对应的是黄色，抱歉我标错颜色了，是绿色的部分，这样。然后再来 OpenSBI 的部分会是有这些讯息，它会在这边，然后这些讯息就会给一个很完整的platform 相关的讯息，它有 platform 相关的资讯，还有一些我的 SBI 相关的实作的版本，还有这个 OpenSBI 用的 OpenSBI 有支援哪些 SBI 的 extension 在这边，然后这边有一些 PNP 相关的设定，这个也都是RISC-V 世界里面定的一些规则这样。然后这边也会包含一些刚才提到的有各个 extension 可以选，那这边就是一些 optional 的 extension， 那这代表是这个 QEMU 的 virtual board 是支援这些 extension 的这样。然后最后深蓝色的部分就是会跳到 uboot proper 的部分这样。好，那我们接下来再来仔细的看一下刚才这个指令执行下去会有哪些过程在地下运作这样。那一开始的黄色部分是 ROM code， 那 QEMU 本身就有带一点 ROM code， 大概会是长这个样子。然后这边的指令后面可以减 S 减 GDB， 这边就可以让你透过后上的 GDB 连进去看 目前的 QEMU 执行了哪些东西的，那就是提供给大家来做参考。然后这边实际上 QEMU 的 ROM code 蛮简单的，它就是做一些事情，然后最后要跳到某一个位置。然后一开始我们的 U 部 SPO 刚在这里这个减 BIOS 的地方，它就会被放在这个位置上，所以它做的事情就是让4颗 hard， 刚才我们减 SMP 这边的4颗 CPU 就直接跳到 ROM 上面，然后跳到 U 部 SPO 上面，那就完成了 QEMU ROM code 要做的事情。那接下来是 U 部 SPO 的部分。那 U 部 SPO 的部分，它主要的任务就是要把后面2个 OpenSBI 跟 U 部 proper 带起来，这样。然后，所以这边会是 U 部 SPO 的 output。执行完这边的过程之后 ，U 部 SPO 就会 print 出这个讯息。那里面实际上做了哪些事情？大概会是它会从 start 开始，然后先执行一个 heart 的 lottery。heart 是指在 RISC-V 里面就是指 CPU 的意思，这样。然后它做 heart lottery 的意思是，我要从这4个 core 随机选一个 core 出来继续执行。那剩下3个 core 就会直接到 secondary heart loop 那边 parking， 就在那边等这个 main heart 继续往下执行。那 main heart 要做的事情就是它会拿 DTS 出来，然后看有哪些它需要用的东西，然后来把 driver init 起来。然后这边要 init driver 的意思是因为它可能要去存取SD 卡上面的东西啊等等的，所以它会需要做一些 driver 的 initialization 这样。然后做完之后，它就会看它接下来要 boot 的东西在哪里，然后把它拿出来，然后最后再跳过去。那在这个阶段，它会拿的是刚才提到的那个 U-boot IPB， 它会被放在这个80250的位置。一开始我们下的那个 QEMU 的选项，那接下来会被这个阶段，它会把这个 U-boot IPB 分解成2个，一个叫 U-boot proper， 一个叫 OpenSBI， 然后放到相对应的位置上。然后最后这个 boot hard 会执行这个 invoke OpenSBI， 然后这个阶段它就会透过 IPI， 就是 interprocessor interrupt， 它会用 software 的方式送一个 interrupt 给这其他3个在 parking 的 core， 然后最后他们就会都跳到 OpenSBI 来执行这样，然后 U 部 SPO 的阶段的任务就完成了这样。然后他们都跳到 OpenSBI， 那接下来是 OpenSBI 的部分。OpenSBI 在 U 部在 RISC-V 里面就是要提供一些 MO 相关 runtime， 可以让SMO 的软体来存取的，然后所以它会提供一些 interface。那在这边要做的事情，它就是把那些 interface 所需要的 data structure 初始化好这样。所以在这边它会也是选好 boot hard， 然后接下来会分2边。然后 after hard 就会直接到 SBI 里面的有一个 extension 是在做CPU 的管理的，所以它就会在那边等，然后其他的main hard 就会继续往下执行，然后把所有东西都初始化好，然后最后它就会跳到下一阶段的 U-boot proper， 下一阶段的那个 bootloader 这样。那可以注意到的是，就是接下来的这一段 code 就会都是由1颗 heart 来执行了，所以在 U-boot proper 里面是只有1颗 heart 的这样。然后在 U-boot 的这个环境里面，其实也是没有 interrupt， 所以所有东西都是 polling 相关polling 的机制这样。然后在 U-boot proper 里面要做的事情就也比较单纯。然后这边它会做一个 relocation， 比较特别的是它会做一个 relocation， 它做的 relocation 是为了把中间那一段 memory 空出来，它会把自己 relocate 到 memory 的高位，然后所以目前有留的 runtime 是这个 OpenSBI 跟这个 U-boot proper， 然后他们分别在 memory 的2端这样，所以中间就可以来放很多东西，比如说你要放 kernel， 比如说要放 root file system 这样，所以然后 U-boot 也提供很多的指令，就如果大家有事的话，在这边可以打 help， 然后就会列出所有 U-boot 支援的指令，然后很多指令都可以用来 load 的 kernel 或你想要跑的 code 上来，这样。那接下来就会执行最后就会进到这个 hash 的 shell， 就是 U-boot 它的本身的 shell 这样。然后这就是到 U-boot 这个部分这样。然后如果接下来是跑 Linux kernel 的话，大家可能会好奇，就是这3个 core 最后什么时候进 kernel？ 那这3个 core 如果是跑 Linux kernel 的话，它会在 kernel 里面有一个叫 setup SMP 的部分。 它在这边也会送一个 IPI 给 other heart， 然后 other heart 就会在那个时候才真正进到 kernel 里面这样。那这一整段就是U 部整个 boot flow 的过程这样。没错。那 U 部其实不只有 boot loading 的这个功能，那U 部还有很多有趣的可以研究的地方，像是 U 部在 RISC-V 这个 port 里面啊，它 U 部 proper 会需要被 pre-link， 它 pre-link 的意思是在它编译的阶段就会有一个 RISC-V 的 loader 帮它里面的一些符号做完 relocation 这样。那为什么？就如果大家有兴趣，大家可以再研究一下，那是有趣的地方。然后 U 部 relocation 也是一个有趣的地方，它是在刚才有提到，这一段就从 U 部 proper 一开始从这边，然后会把自己搬到这个位置。那它搬这件事情具体怎么做，那也是一个有趣可以研究的地方。这样，然后还有 U 部的 driver model， 它是就是有点像 kernel 的 device driver 相关的东西一样，这样。那大概是这样的介绍。那后面的 reference， 这个 reference 是先前在 RISC-V Summit 有报的，有厉害的工程师报的那个 boot flow， 那大家也有兴趣的话可以参考一下。然后这边是公司的网站，这样如果大家有兴趣也可以来看一下。那我今天的报告到这边，感谢大家。
咱们现在先休息个10分钟，这样如果有问题关于这个站的一些内容 ，We're taking a 10 minutes break. If you have any questions, you can come up to us. Thank you.
隔壁教室还有一些就是隔壁教室的食物还有剩。那如果刚刚有伙伴来不及就是吃到晚餐的话，也可以到进来去隔壁教室享受看东西。谢谢。
有，
我先问一下，
感谢。
我借个麦克风。
哦，对，麻烦你，拍这，
谢谢，
谢谢，
对，你可以拍个放。
对吧？
不用想这样子啊，我是想说，谢谢，来领词。
小零食那个点到了，又我都是谁来或者是我们有 Orange Crab， 就橘螃蟹，然后这边有这个也挺不错，打 freeze， 你可能要解析度要拍那种，可能对比度再调一下之类的。然后它其实像老贵，就其实你就是甚至是可以有这种，就如果你有装瓦是有 GPU， 没有，对，就是之前表示它其实是有。你可以，就是它是足够你去切个白幕出来，然后这边这个是它的那个 console， 对，就是早年那种电脑的感觉，就是你不同的大小会有不同的 solution， 对 ，OK， 对。Or you can buy the CBA 6. Sorry. This gentleman for free. This gentleman is asking that whether which FPGA board is the best for learning the RISC-V designs, and I would say that Genesis 2, right? Yeah.
OK，直接比讲就
好，
顺风了吗？
可以，好，
马上做。
谢谢。嗨，Hello。嗨，OK，那我就开始喽。好，我是今天8点的讲者，然后我接下来要讲的是RISC-V kernel mode vector。那这个 kernel 指的是 Linux 的 kernel。那主要 focus 的主题呢是在于说Linux kernel 本身要怎么使用 vector instructions 这样子。那我们都知道 vector 这个新的 extension 呢，它加了一些registers。那作为一个 operating system， 当有新的 register 出现的时候呢，最基本要做的事情，要 support user space 的时候，我们需要做 context save 跟 restore， 在做 context switch 的时候。那这个是指 user space 的 vector。那我们要在 kernel 里面也要使用 vector 的话，一样也会有这个新的 context 要怎么去做存取的问题。那我今天的主题会 focus 在这边。然后我是 Andy， 来自一个大家都不喜欢的地方，对。然后对，然后因为我现在也不在那里工作，所以我不需要讲是哪里。对，好，下 ，OK， 那我今天会介绍的事情是，在kernel mode 里面怎么去使用 SIMD， 那也就是vector extensions 这样子。那还有就是为什么在 kernel mode 里面使用 vector， 尤其是 preemptible 的 vector 的时候是有好处的。然后会提供一些 case studies， 就是现今的架构他们是怎么实作在 kernel mode 里面的 vector， 的 SIMD 这样子。那接下来会介绍 RISC-V Linux 里面怎么去实作 preemptible kernel mode vector 这样子。然后当我们有了 kernel mode vector 之后呢，会想要做的一件事情就是如何使用 vector 去加速整个 kernel space。那有一个很明显可以用来 optimize 的地方呢，就是user copies 这样子。那也会提供一些 benchmark， 然后还有之后可能可以发展的方向这样子。OK， 那 kernel mode SIMD 在 Linux 上面呢，其实是被限制使用的。那主要原因有几个。Linux kernel 它希望使用就是最少量的 register file 这样子，那这样可以极大化的就是把 compatibility 顾好，因为不一定每一个 SOC 都有 vector extensions， 然后有些甚至没有 FPU， 所以如果我们只用最少量的 register files 的话，会有比较好的 compatibility 这样子。那再来就是latency 的问题，就是当我们在 exception entry 跟 exit 要存或是读的 register 量比较少的话呢，它的 latency 就是我们在处理 interrupts 或者是我们在处理 mode switch 的时候，它的 latency 会比较低这样子。那还有一个好处就是说，当我们把多余不需要使用的 units 关掉的时候呢，它可能会比较省电这样子。那在这些考量之下呢，如果我们在 kernel mode 还是想要使用 SIMD 的话，要怎么做？ 因为我们知道 kernel 里面有一些网络相关运算或者 file system 相关的运算，它会有在我们使用 SIMD 会有一些好处，就是譬如说算 hash 啊，或者是加减密等等。那所以如果真的要使用的话，通常我们的做法是这样子，就是第一步我们会 disable preemption。那想大家应该都知道 preemption 是什么。对，好，那对，他会先把 preemption 关掉，因为我们不希望我们不希望多去存或者是 save 跟 restore 这些 vector context 在我们 kernel 自己正在使用的时候。所以说我如果在这个kernel 本身在使用的时候不去做 context switch 的话呢，我就不需要再去顾虑说我在使用到一半的时候，有 context switch 的时候要做什么事情，这样子要去多save restore vector 多余的 register context 这样子。然后当我们关完 preemption 之后呢，我们就可以开启这个 SIMD 的 unit， 然后去跑这个 SIMD 的 code 这样子。那我这边会写它是 non-nesting way 的意思是说，因为 kernel 本身它是可以 nest， 就是当我们在 kernel 的 thread context 的时候运行的时候，这时候有可能会有 interrupt 来。那 interrupt 完之后会有时机会去 serve 这个 soft IRQ。那这个 soft IRQ 它是 nest on top of kernel thread context 这样子。那一般来说，如果我们 kernel 本身正在 thread context 里面使用 SIMD 的时候，这时候如果有一个 hard interrupt， 然后紧接着 soft IRQ 的话，在这个 soft IRQ 里面，我们是没有办法使用 SIMD 的。那这会有一些问题，因为有些 networking 的处理，它其实是在 soft IRQ 的 context 里面去执行的。那我们都知道 networking 会有一些适合使用 SIMD 的时机，这样子。OK， 然后在 Linux 里面，我们需要使用 SIMD 的时候，如果是 ARM 的架构的话，我们可以 call 这个 kernel neon begin 跟 kernel neon end 这两个东西，它会帮我们关掉 preemption。然后在 ARM 里面的话 ，SIMD 本来就是打开的，所以它会帮我们关掉 preemption， 然后做一些必要的事情。因为我们知道，也许我们在 user space 本身已经在使用 neon 或者是 vector 之类的 rich 的 file。那我们如果在 kernel 里面也要使用这些东西的话，我们会需要把 user 的东西存下来。对，那这个 kernel neon begin 跟 kernel neon end 就在做类似的事情，这样子。OK， 好。那刚刚提到我们在 run kernel SIMD 的时候，最主要几乎都是以就是 non-preemptible 的方式去做，就是在 kernel 使用这些东西的时候，我们会把 preemption 关掉，然后希望尽速的把这个东西完成之后，再把 SIMD 关掉之后，把 preemption 打开，这样子。好，那这会有一个小小的问题，就是我们都应该不喜欢把 preemption 关掉，对，因为把 preemption 关掉的话，可能会变得没有，就是比较反应迟钝一点点这样子。当我们有很多 task 在进行的时候，那以现今来说，有一些 networking 的 SIMD code 它会处理到一半之后把 SIMD 关掉，然后去做一些 voluntary 的 schedule 的 call， 让我们去主动让出这个时间这样子。那这样子就对写程式的人来说也是比较麻烦一点，因为他可能不知道这段 code 会执行多久，或者是 对，它不会在一个理想适合的时机，由 kernel 的 scheduler 自己去决定说什么时候要去做 context switch 这样子。对，那所以说，如果我们可以用某种方式把 kernel mode vector 变成 preemptible 的话，我们会有一些好处。最直接的2个好处就是像是在这边提到 software rate 或者是一些 networking 的运算，或者是我们要 copy 很多 user data 的时候，我们可以直接使用 vector optimize 的 code 去帮忙这样子，然后也不需要顾虑说我们执行了太久的 vector 会让 kernel 变得反应迟钝这样子。OK， 好，那这边是几个 case studies， 就是在我们在实做 RISC-V 的 kernel mode vector 的时候，看到了一些情形。那在 PowerPC 的话，他们的 internal SIMD 是 non-preemptible，包含 x86 也是，当时的 ARM64 也是 non-preemptible， 但是后来改成 preemptible 这样子。那在 sub-hierarchy context nesting 的话，前2者都是 non-nesting 的，所以说在 sub-hierarchy 里面的时候，我们会没有办法。假设我们在原本的 kernel thread context 就已经使用 SIMD 的话，在 sub-hierarchy context 会没有办法使用这样子。那在 ARM64 的话，它是如果我要使用，我就马上把 kernel 的vector context，sorry， 我这边用的 term 不太对，就是 kernel 的 SVE context 存起来，然后我一结束使用 kernel mode 的 neon 的时候，我就再把 SVE neon 的东西 restore 回去，这样子。那我每一次使用都要去存，每一次使用结束都要去读回来。对，那在 user copy 这一块的话呢 ，PowerPC 它有一个VNX optimize 的 copy， 那它的做法也是就是要 disable preemption， 然后使用 VNX copy 这样子。那还有一个 scalar fallbacks， 那这个 scalar fallbacks 的意思是说，因为它 disable preemption， 然后 kernel 在去 access user space data 的时候，我们知道 user space 的memory 是有可能发生 trap 的。那我们再去读或是写这个 memory 发生 trap， 它可能是因为它后面的page 还没有被 allocate 出来。那这时候如果 kernel 要去配置这些记忆体出来的时候，它有可能会让这个 process 去 sleep 这样子。那我们如果在 preempt disable 的状态下是没有办法 sleep 的，所以当 preempt disable， 当 PowerPC 想要使用 vector optimize 的 copy 的时候呢，它踩到了一个 trap 之后，它会回到 scalar 的 instruction 再去执行那个就是回到 scalar instruction 之后就不需要 disable preemption， 那这时候再重新去执行一次就可以才可以完成他们想要 user copy 这样子。那 x86 他们的 copy 蛮有趣的，他们用1道 instruction 就可以完成 copy 这样子。那里面应该是有一些魔法这样子，对，就是这就是 x86 厉害的地方。对，那再来是 ARM64 的 low store 蛮有趣的，他们是可以 low pair 跟 store pair， 就是它可以一次 low store 在一道指令里面 low store 2个 register。那其实这个意思就是说，它有一个128 bits 的 effective length， 就是我可以一次存比较多嘛。那 vector 它其实也是它的核心概念也是一次做比较多事情这样子。OK， 那所以我们就可以想一下 RISC-V 可以做什么。这其实跟 RISC-V 本身没有太大的关系，就是 我们想要怎样子比较好，软体上，我可以说，我全都要，就是我想要它可以是 preemptible，然后我也想要它可以 nesting，然后既然是 preemptible 的话，很遗憾的，因为 RISC-V 没有 low store pair，对，我不知道为什么，但是所以我希望它的 user copy 是 vector optimized 的 copy 这样子。那 sub-IRQ context nesting 这一块呢，其实有方法可以做比较好，譬如说我在第一次使用的时候去存nested 的 context，然后在 exception return 的时候再去 restore nested 的 context 这样子。那就不用在每一次 API call 就是 kernel vector begin kernel neon begin 或者是 kernel neon end 的时候呢去做 save 跟 restore 这样子。OK， 所以这是 RISC-V 想要打我们再重新设计一个in kernel vector 的时候想要达成的目标这样子。那接下来会讲它是怎么实做的。OK， 那这边有3条线，就是最底下那条线是我在 user 的时候的时间轴。那 user 进到 kernel 通常是透过 trap 进到 kernel， 所以中间第2条线是 kernel 这样子。那我可以用滑鼠吗？可以。OK， 我们进到 kernel 里面，假设我想要使用 vector 的话，在 RISC-V 这边我们是用 kernel vector begin 跟 kernel vector end 去加要使用 vector 的区段这样子。假设我们 user 都是有在使用 vector 的情形下 ，kernel vector begin 它要做的事情是它会 save user 的 vector context。那然后去执行 vector 的 instruction。这时候我们不关 preemption， 所以有可能会有 interrupt 来，或者是任何 kernel 觉得可以做 context switch 的时机。那当我们要做 context switch， 如果是 trap introduce 的 interrupt 所谓 trap introduce 的 context switch 的话呢，因为 kernel 做到一半。不知道发生什么事，发生了 trap， 然后要做 context switch 了，这时候它就需要存 kernel 的 vector context 这样子。那当我 switch 回来之后呢，我也需要做 restore， 因为我这个 trap introduce 的 context switch 回去是一个 trap return， 然后回到刚刚 kernel 正在使用 vector 的 context 里面。所以我这个时候要 restore vector context 这样子。然后这边有一个比较有趣的地方，就是我们什么时候去 restore user 的 vector context， 就是最下面这条 user 的。那我们可以在 kernel vector end 的时候去 restore，但是这样子就会变成是说，我下一次要在 kernel vector begin 要在使用一次 vector 的时候，我还要再把 register 存下去一次这样子。所以说我们在这边是延后到真的 return to user space 的时候才去 restore user 的 vector context 这样子。那我们要在这边要做的事情就是我们必须要在trap entry 跟 trap exit 的地方呢去做一些有一点像是 context tracking 的东西的 code 去帮我们去记录说什么时候要restore 什么东西回去这样子。OK， 然后其实如果我们要再把它扩展到 soft IRQ context 的话，其实方式是一样，就是当我们在soft IRQ context 要执行 vector instruction 的时候呢，我们要做的事情是直接的也是一样，就是第一次使用的时候，我们把 kernel 的 vector context 存起来。 那在 SubIRQ 里面呢，我们是可以关 preemption 的，因为 SubIRQ 本身就不会有 context switch， 所以在这时候我们会关 preemption 去做。那在这个之后，我们就不会再去允许就是nest 更上面一层那的去使用 vector， 因为在现实的 Linux 中也不存在这样子的使用情境，这样子，所以最多就是叠2层在 kernel 里面。那也是一样，我们等到 exception return 的时候才会 restore kernel 的 vector context， 然后这时候 restore 也是会就是因为下一道 kernel mode 的 instruction 就会使用 vector， 那我们就马上 restore 这样子。OK， 然后可以 OK， 然后我们要怎么去 optimize user copy？ 其实就如同刚刚提到的，就是 user space 的 memory access 有可能 fault， 然后发生 fault 的时候有可能去 sleep。那我们要做，如果我们是在允许 preemption 的情况下使用 vector 的话，我们就不需要担心这件事。那在 kernel 里面也有一个 config 是不允许 preemptable vector， 那这时候我们一样跟 PowerPC 就会有一个 scalar fallback 这样子。OK， 然后这边是 benchmark， 然后这个 benchmark 是从公开可以找到的资讯拿的 benchmark。那这是 Sci-Fi 的 P470， 然后模拟的 frequency 是2 MHz， 然后 LC miss latency 是85 nanoseconds， 然后上面那一张图是 secret， 就这2张图都是 secret test 这样子，然后上面是 without preemptable vector， 就是我们在使用 user copy 的时候都把 preemption 关掉，然后使用 scalar fallback。那我们可以看到，就是绿色的线上它的有比较多高 latency 的情形出现这样子。那当我们使用的 preemptable vector 的时候呢，可以看到它的线几乎是就是它的反应几乎是跟 scalar copy 是一样的这样子。那这边有 netperf 的 total bandwidth， 那可以看到使用了 vector 之后，它带来的好处是很显著的，就是几乎有就是5000到8000这样3000 megabyte per second 的megabit per second 的improvement 这样子。那我们使用 preemptable vector 跟不使用 preemptable vector 可以看到的是，它们带来的效能差异是不大的，所以 preemptable vector 并没有为throughput 带来负担这样子。OK， 那有一些可能的 future works， 就是第一个当然是既然我们现在有 preemptable vector 的话，我们可以增加更多 vector optimized 的 copies 这样子，然后再来是 auto vectorization。那这边是一个蛮有趣的议题，就是我们要怎么让 kernel 可以更广泛的使用 vector。那这边有一些可能可以执行的方式。最简单的当然就是在每次 exception entry 跟 exit 的时候呢，我们就把 vector register 当做 general purpose register 来存这样子。那对，但是这样会带来 stack 的一些负担。对，下面还有一些其他可能可以的方式这样子。然后对，我今天OK 好，那这下面这2个 approaches 都会需要 compiler 的帮忙这样子。那就是我们可以只存部分的 register， 然后借此来减少 stack 的负担这样子。那有一个方法是我们存比较少量的 vector register， 然后在 code gen 的时候限制 compiler 只使用一部分的 vector register。但是这样子会有一个问题，就是说我们如果是存如果是 RISC-V 的 vector 的话呢， vector length 是非常可变的。对， 那有时候也可能会大到我们如果只存 V0 V1 的话，也太多了这样子。那或者是我们可以只使用 low 128 bits 的 vector 这样子。那在 kernel 这边可能又需要很多 compiler 帮忙，这边不是我常懂的东西。对，那还有另外一个 approach 就是，如果我们 compile 这个 kernel 2次一次，然后放到同样都 load 到 memory， 然后有一份 kernel 是 auto vectorized 的，然后有一份不是，然后我们在 exception entry 的时候去决定现在这个 context 是不是可以使用 vector 这样子来去做切换这样子。
上最后的一个。
就 OK 好，就第三个 approach 就是说，我们把整份 kernel compile 2次，然后都同时 load 到 memory 里面去，然后对，这是一个很天马行空的方式，对，它会可能需要一些link 的改变，就是说我们有些 data 是2份 code 必须要共用的这样子，对，然后还有
好像有点像 base kernel 被 kernel 那种感觉。没有，这只是闲聊而已。就是因为我记得有个机制叫 back kernel，就是这有可能借用那边的东西，不确定。
我对那边不熟也许我待会再跟你讨论一下。OK， 好，那对，今天大致上到这里，如果有什么问题的话，可以。
收几位？跟对不起，问题跟没有关，但是我对 RISC-V 不熟，我想报识一下。这边对我是你要那像以前你要在8的 USB 到19的 USB SE 做 SE，那像 RISC-V 有相关这样子进展的一些关于时间权。
OK，RISC-V 的 P extension 对应到的是 Neon，RISC-V 的 Vector extension 对应到的是 SVE 跟 SVE2，然后现在 RISC-V 有一些大家各大厂商应该有在做一些跟 SME 相关的 extension 这样子。
现场还有其他问题吗？
OK，
问受的案例大部分受是把这个它那个定义的状态存在
不是，因为我们在有 kernel mode preemptible vector 的情形下 per thread 会有自己的 kernel vector context，所以当我们要存的时候是存在 per thread 的 kernel vector context 里面。然后这边有一个比较简单暴力的做法，就是我在 exception entry 就存 vector context，那这样子会有的可能的负担就是，也许我在 sub IRQ 里面根本没有用到 vector，那我们就多存了一次这样子。
所以这个是在如果有受可以有发有自己的指令，然后才会去做你刚才说的那个
对对对。在 kernel 里面，我们要使用SIMD 的时候，都会需要 call API 把东西开起来跟关掉。每个 architecture 有自己的事做，有些 architecture 会要关 preemption，有些不用，那就是在 architecture specific 的 code 里面要去做这件事情。
谢谢。
谢。
我最后快速去往分它走向一次。 电池要带跟你之后，今天可能东西已经坏掉，所以电池其实有一些行业可以用8六的方式可以去编一个 smoker， 那可以用这个下进去做一些收尾的动作。但是其实我记得好像像那种话一些重要的要进去，就是它今天有时候会主动在看跟我们做事。我说这感觉好像可以偷偷来用。我遇到几次找准备。
啊，谢谢。
Actually, we made task for the spot, so we go back for capturing.
Sorry. 好，That's for you.
只是防止这么高。
Yeah.
这可能不行。可以吗？还是在这里？
OK。
外套可以吗？好的，谢谢啊。
谢谢。
Oh, great. Hello, my name's Katie. I'm from the Programming Language Lab at National Tsinghua University. I'm a PhD student there. And I know today you might have seen I'm doing a talk on AI compilers and RISC-V compilers. We are a compiler lab. However, I do hardware software co-design. So today we're going to be talking about a custom RISC-V extension and the hardware side, as well as the LLVM support we've added. Also, I didn't know we'd talk about this today, but earlier on, I'd like to thank Flo. We're talking about CVA6 a lot, so thank you for the introduction already. It's of great help to me. So, before I get into what we were doing, we were recently in Germany at EuroLLVM, and we're going to be in ES Week next month. But before I get into what we were doing there and what we're working on right now, I'm going to do a quick overview of just a return of vector architectures, because that's what we're going to be talking about in general and what our main goal was. Can I move this mouse? Yeah. And then we're going to go into OCP formats, including microscaling formats. So that's, if you've heard of sub-floating point 8, so floating point for 8, 6, and 4, how those two can be combined together, and then how we did that within their scalar instructions, because we started on a scalar core, just much easier to implement there. And then we stopped at floating point 8, and now we've moved on to a vector core, so a coprocessor called ARA, where we've combined them together, but the architecture and the ISA design there was very, very similar, so we're going to pair them together. If there's any questions within this whole entire thing, please just ask me. I'm always happy to interact. So let's talk about the history of vector architectures and why it is that nowadays they're coming back. So you probably know back in the 1960s, that's kind of when they started to become famous with things like the Solomon project and the ELIAC, and then eventually Cray, which was at the time the fastest supercomputer in the world and is very similar to a lot of vector processors we have nowadays. You've got your vector register files, you've got separate functional units, focusing really heavily on parallelism, but then as silicon gets cheaper, they start to lose popularity until we hit a power wall, which is the last decade or so. We've come back to vector architectures because what we're looking for is efficiency, right? Right. So, what are we looking for in particular? Why vector over scalar? So right here, this is a floating point instruction that was run on CVA6, which we were talking about earlier. And if you see, this is the power consumption in picojoules. Just the instruction fetch alone is more than 10% of the energy that we're using. And so when we're using a vector architecture, we don't have to worry about that nearly as much. What we're trying to do is we're trying to reduce the amount of energy that single instruction will use. So when you're running 5 instructions, like with dot product, only 9% of that energy actually has to do with computation, right? So, we'll move on. What does this have to do with floating point? And what does this have to do with sub-floating point 8? So right now, you're probably familiar, floating point 64, 32, 16. And we're trying to reduce those further and further because the smaller we can get those, so to floating point 8 to floating point 6 to floating point 4, the more data we can process per cycle, and the more we can fit in registers and in the cache, and we can boost the throughput. The problem is in RISC-V, we don't have, like our IEEE standard, we have something called OCP, and we don't commonly see it in processors nowadays. So CVA6 actually does have one. It has E5M2, which is one of our floating point 8 supported. But as far as microscaling formats go, which are these right here, they're not commonly supported in anything. And we need to make sure that not only do we have a standardized form for them, that the standardized form and these formats actually give us the results we need. We don't want to lose accuracy or anything when we're reducing down from like a 32-bit floating point into floating point 8, floating point 6, floating point 4, because that kind of just negates all our work, right? So for standardization, what we've got is the Open Compute project, which has two different specifications. OFP8, which is just for floating point 8, it's not scaling. We've got E5M2, which is what I was saying was supported, and E4M3. And then we've got microscaling formats, which do use a scale, and this has for floating point 8, floating point 6, floating point 4, and int8. So what we're starting out with are just the OFP8 specification, much easier to implement, and plus E5M2 is already in a lot of devices. And then when we're moving down to floating point 6 and floating point 4, we're going to focus on the microscaling. So what does this look like? What I was saying before is that it's very important that we're not losing precision, we're not losing accuracy, and that when we're going down from 32 to 8, 32 to 6, 32 to 4, we're not changing our data, right? We don't want to make our computations incorrect. So luckily, there's a lot of people who have tested this stuff out. So we have the results that we need energy-wise. You can save up to 30% of your energy. And there's been studies that show that 90% of floating point operations can be safely scaled down to 8 or 16-bit formats. So this means we're not losing accuracy with those values. I have a bunch of examples of it. I'm not going to read through them, but these are for the microscaling formats, not for the OFP8. But these are just examples of times when there's been training with these values and that they have not lost a lot of accuracy, or they've lost minimal accuracy, but not enough to highly impact the data. Okay. So I know I was just talking about vector, but it's much easier when you're making a new ISA, it's much easier, at least in this case, when we're testing out adding new sub-floating point 8. That's what we're calling these sub-floating point 8 values. It's much easier to do it within a scalar core. So what we started out doing was adding floating point 8 E4M3 into CVA6's floating point unit called CVFPU, and testing that and making sure that we have compiler support for it and that our ISA design and our modifications work. Once these work, we moved it over into a vector coprocessor coupled with the same exact processor, and that's what we're working on now to extend to also use the microscaling floating point 4 and floating point 6, because that's really where we're looking to get that performance improvement that we're looking for. And this is just where they're at right now. If anyone's going to ES week, the end of September, I'll be there too. It's great. So the design of this is every single floating point instruction now has a new opcode, which is something we changed on the new version for the vector because this adds a lot of pressure. But in our first case, in our test one, we have, instead of fadd, we have sfadd. And why is this? So instead of having your format in your instruction, what we do is we use a pseudo instruction called SSET, which then breaks down into, this is CSR write with no read, which will then write to our floating point CSR. So up top is what the floating point CSR looked like before I touched it, before I did anything with it at all. Afterwards, you can see we added two fields called EFT and SFT. These, most of the time, will correspond to SFT being your source register format, while your EFT is your destination register format. So what this SSAT and pseudo instruction does is it allows us to decide what values we want to hold in those fields in that floating point CSR. So you only need to run it once. And when you decide what you want your source value to be, your source format to be, and your destination format to be, you run that, and then all following instructions that have the prefix, just to do with opcodes, but the prefix, just when you look here, of SF, so our subfloating point, will then use the source value stored in the FCSR and the destination value stored in the FCSR. Of course, if you're not running that many instructions, this is kind of a waste. But if you're running a lot of instructions, it's not a big issue because you're using 2 instructions to just set this value. And I'll show you what that looks like hardware-wise. But it's a little bit on the compiler side. So they added support, my colleagues added support in LLVM for this. So there's backend and code generation, instruction support, pattern matching, and you can see here on the right that you can see the compile flow from C to assembly. So you can see where it started out, where they've set E4M3. You can see it as SSET insert with the pseudo in front of it, so our pseudo instruction, and then you can see how it breaks down to a CSR WI, right? And this was a pretty small cache, but we did do some testing with for verification just to make sure everything was working in Spike and using Gem5. And we had about 20 times fewer L1 cache misses, which is what I was talking about earlier, where we could reduce cache misses, increase the cache hits just by reducing our floating point format to a smaller format, right? Okay. So now we're going to put it in the hardware. Flo was talking about this earlier. This is CVA6. It's wonderful for, just if you're doing educational purposes and everything, it's pretty easy to modify. You can see here, this is not actually a new path, but in red, that's the path that the stored values of EFT and SFT travel from the CSR registers into the floating point unit. And from there, they're just processed like any other instructions. Again, there was a lot, since we added new instructions for every single sub-floating point value. Well, really, they're not that much different than just a regular, like SF add is not that different from F add. In the next iteration, in the vector section that we'll be talking about next, we reduced that. We removed that completely, and we just reuse instructions. So, yeah. But you can see that path is actually not a new path, but that's the path that those formats are traveling to. And those formats are only used when it has the prefix of SF. Right, and it wasn't a big increase, but this was just the addition of E4M3 because there was already support for E5M2, although the subfloating point 8 does support E5M2. Okay, so architecturally, those EFT and SFT are the same exact thing when we enter the vector instructions. So instead of using the floating point CSR, we have V-type, which is our vector CSR. It's stored in our vector processor. Up top is what it looked like before, and then below you can see again EFT and SFT. That process exactly the same, but you see one more field of VSF. This is so that we're no longer adding a new instruction for every single subfloating point vector, like addition and multiplication. You can just reuse them completely, and instead we're using this as a flag to either turn it on, saying use our formats from SFT and EFT, turn it off, don't. We're also looking at other techniques that wouldn't require us to have these CSR WI instructions at the beginning, just because that is still a cost, when you're adding new instructions, but for right now. Yeah. So conceptually, pretty much identical, but instead of having new instructions, new opcodes, everything like that, we're reusing them and just having one more type of set, one more type of CSR write that either turns on the use of SST, EFT, or turns it off. So pretty much identical. In addition to having to decide what the values of SFT and EFT are, we also still need to make modifications to our element width. So we have an element width of 8 already, but we would need to add 6 and 4, just so we know. As a little note, ARA, which is the name of the vector coprocessor we're using, has support for E5M2, not E4M3, but there's infrastructure there. It can't be used, so technically there is support for it, but it can't be used because CVA6 doesn't support it, and also because there doesn't seem to be really a way to turn it on. I mean, there is a way to activate it, but it's not. You would have to make an instruction that would then activate it. Right now, it's awful everywhere, but that makes it very nice for me, at least. Yeah. So what does this look like in terms of hardware? Great, the fun part. Okay, so this is Cheshire. Also was mentioned earlier, this is a system on chip with ARA and CVA6. So this up here is CVA6 that you just saw, our scalar core. And this is ARA, our vector coprocessor. So ARA can't be on its own. It does not have access to its own instruction cache, so it needs our scalar core up here so that it can get instructions, right? I'll go a little bit, I don't know how much time I've spent, so I'll go a little bit later telling you kind of the path these travel, but I'm a little bit worried about how long have I talked. I'm okay.
We have 15 minutes left.
Fabulous.
You were the last one, so just go for it, I guess.
Oh, this is wonderful. Okay, thank you. So we have to pair it with CVA6. A great thing about ARA, which I'll go a little bit more into detail afterwards. So ARA is where all our computations happen. We have shared functional units of our mask, our slide unit, and our load and store unit. And then we have something called lanes. And these lanes are what hold our floating point unit and our ALU, and also chunks of our vector register file. And we can configure this anywhere from 1 to 16. You will see later on that mine is configured at 2, and on my device it takes up the whole entire thing. It's massive. And if anyone wants to see it later, that tiny computer up front on my desk runs all of this. You can actually see how many elements. It's awesome. So it defaults at 2. It's what we're keeping at for now, mainly because I can't make it more than that. And you can also, this little bit in red, you can expand that over and over and over again, up to 31 times. Again, I don't have space for that on my FPGA, but like theoretically you could. So officially, the only board that this runs on, if you go to the Cheshire GitHub page, is the VCU 128. I've now configured it for the VCU 102 because that's what I have access to. But again, I can only do it with 2 lanes, so you might be better not using that. And also, if anyone ever wants to run this, I have a big guide. Oh no. That's not good. Well, I've lost like half my slide. I don't know if I really need it. I can just explain. It's okay. We're missing a diagram down here, which might make this a little bit hard, but like, I think I can do it. Okay. So let's just talk about an instruction flow. So CVA6 is not actually CVA6. That's just our base name, right? What this actually is CV64A6. So this is 64-bit variant of core V, so CV, application class, 6-stage pipeline. You probably only see 4 up there. Front end has 2. I don't touch those two stages. We don't worry about them. So normally, if we're doing a scalar core, we have our instruction cache. We're just going to go to the decoder. We're going to go through this. We're going to go, you know what, whatever. It doesn't matter. We're talking about vector here. So when we want to use ARA, we still start an instruction cache, which is why I'm saying you can't have vector on its own. We still need this instruction cache. It goes to the decoder. It gets partially decoded. And it sees, oh, this is a vector instruction. So it's going to send it here to our accelerator dispatcher, because it's also an accelerator. ARA is an accelerator. And then it sends it to ARA. Well, first it has to go to a scoreboard, and it gets to the top of the scoreboard. It's like first in, first out. And it says, okay, send this instruction. Dispatcher looks at it and goes, okay, we have no issues. There's no exceptions. There's nothing illegal. I can run this instruction. This coprocessor ARA says, okay, I can run this. You're good. It tells CVA6, I can run this. And as far as CVA6 is concerned, the instruction is done. The instruction is not done. It has not been completed. But as far as CVA6 is concerned, it's done. So it can do its next thing. It can run another instruction, no issue. Then it gets into ARA. I should have had these pictures. This is going to make it real hard. Okay. So maybe the next one will help. I might be able to use this to help.
Because actually we have the capture, so you can plug in your computer for this slides. Because you're the last one, I guess it's okay.
It's
Okay.
It's okay. It's okay. We'll get through it. We'll get through it. So one thing we should talk about when it comes to ARA is that it has, not always, but a parallelism of 2 elements per cycle. So when we're loading from our memory into our vector register files, which I said earlier are in each of these lanes has its own, so that's the picture, wherever it is. Each one of these lanes, what we can do is say we're loading 8 elements. We can load them 2 at a time using our load store unit right here. And then we can distribute those elements into our lanes over here. We can do whatever arithmetic we need to do, our computation. Then we can pass it. You can kind of see this description I'm saying on the side. We pass it back here, and then we write it back into our memory, right? But why 2 elements, right? Why are we just doing 2 elements at a time? We're loading 8 elements, so why just 2, right? In a vector processor, why wouldn't we just load all 8 at a time? Great question. So the way that ARA handles vectors is not just with time and not just with space. So all the way on the left, you'll see CVA6. This is our scalar core that we were talking about, right? Here, each one of these, what I'm talking about, is one instruction. One instruction. I've also put, because I know there's probably a lot of software people here, I put a software representation on the right. And then this is our hardware implementation. So for one instruction, what I was just saying is that for space, imagine that's just one cycle. They're all in one row. You could load in with one instruction 4 elements, and then you could send those 4 elements each to a lane each, right? So that would require a lot of space. You'd need 4 lanes. Or you could do it the time way. You could just have 1 lane, but you need a lot more time. So even though you're just using 1 instruction, in your data cache, you're still loading 4 times. So 4 cycles there. So with your space one, it was 1 cycle, great, but you're using 4 lanes, which at least in my case, as I was saying before, I can't use 4 lanes. I don't have space for that. Time. We only need 1 lane. We've got 4 elements. So, but now we've got to wait 4 cycles. But what if you combine them, right? What if you have 2 lanes and then you load 2 the first cycle and then 2 the second cycle? And that's what ARA does, right? And of course, that can be scaled up. This does go up to 16. Technically, it goes above 16, but I do not recommend that. So we could scale that up and do even more and even more. So maybe even in some cases, things like space would be better, but that's the way that ARA works there. And this is what I was saying about the fact that I can't go above 2 lanes. If you look on the diagram on the left, and if anyone wants to see the actual resource utilization of this, I will open it up and you can take a look. It's something like 200,000 lookup tables plus, and that's just for the 2-lane one. And you might see that big gap. This is actually a system on chip FPGA, so those are ARM cores. I can't use that space down in the corner, so I can't touch this, sadly. So the pink is the ARA, so our vector coprocessor, those are all lanes. And then the purple, which is also kind of looking pink, is CBA6, and then the light blue is everything else. You can also see here, just as our hierarchy, you can see taking up this massive amount of space are lane 0 and lane 1 within ARA. And then over here, we've got CVA6, and then you can't see them, but all our peripherals are just hiding down here. Okay, I think that's most of it. If anyone wants any of these things, these are the links. However, I just want to say, Cheshire, if anyone actually wants to run this system on chip, don't just take it from this Cheshire. I shouldn't have just put it up here. You have to find the ARA version 2. If you don't do ARA version 2, it doesn't support ARA. And so you can still do Cheshire, so you can still use this, but it won't have this here. So you'll still have the rest of the system on chip. So if you just wanted to play around with CBA6 and didn't want ARA at all, it could be great. Also, if you just want to play around with ARA, there's an ideal dispatcher mode, so you don't technically need to be using CVA6. I mean, just for testing purposes, don't do that altogether. Yes, and if you are interested in that, I can get that to you. And also, I have a guide. If you do this on Windows, it takes a very, very long time, but I have a guide if anyone's interested, or if they want to know more about the architecture, also, please find me. I have a lot of information, and I like to talk, so that's it. And if you want to contact me, it's right here. Oh, yes. Hello.
I saw your diagram with the baseline future and from error to the I-cache.
This one?
So your error is back with the back to the I-cache.
Yes. So I don't touch that, to be honest. The actual instruction isn't coming from that direction. When it comes to the vector instruction, it's coming from here, the same exact path into what's called the partial decoder, and then into the accelerated. I'm actually not 100%. I'm gonna be honest. I'm not 100% what that's for, but that's not for the instruction. For the instruction, it follows the same exact path as it would on the scalar side. It just goes to the top of the scoreboard and then over here to the dispatcher. We can't use this, at least that I know of. We can't use this to access the instruction cache. If that's not true, someone please tell me, but that I have found, because that would be a great shortcut if so, but I've been told I can only use it from this direction. That's a good question, though. I will look into it more, and if you email me, I'll respond. Hello.
Hello, sorry.
Yes.
Follow-up question.
Yes. Not the same one.
What's the dispatch then? So my understanding CBA6 is a standalone CPU, right?
Yes, it can be.
A code process.
Yes.
How are you connecting them?
Right here.
Because you're sending.
Sorry. Fabulous question. How are we connecting them? Right here, coherent signals. So when it gets to the, I wish I had the other photos. When it gets to the accelerator dispatcher, so do you know what a scoreboard is in this context? Okay. No, so it's like first in, first out, and all your instructions are on there. When it reaches the top, CVA6 will say, we'll send this instruction to ARA through here. It's a request to the dispatcher. The dispatcher will look at the instruction and say, is this valid? If it's valid, it responds. It's just a signal, just responds and tells it it's good. And as far as CVA6 is concerned, the instruction is done. It's not done, but as far as it's concerned, it's done. So all we have are signals that are connecting this. So you written Verilog in terms of, okay, I can show it to you.
What's the difference between sending like your coherent signals connection that versus sending it across the bus to like a completely independent processing unit?
It's not using our main bus. This is,
Yeah, so what I'm trying to say is, what's the difference between, I understand that this point is the main bus, what's the difference between using the main bus and the way you're doing it at the moment? What kind of connection? Is it like an access connection from the CPU to the code process?
I might just have to show you, might be a better way for me. If you want, it's seriously right over here. I can open it up and show you.
Yes, because
Oh, I have to rerun it. It's going to take about 5 minutes if that's okay. I mean, like I have Avado running on my computer.
it's completely okay. It's your trouble completely over.
But I can, yeah, unless other people have questions.
So if it's over,
I can run this in Avado right now and I can show you. I know what you're asking.
Is the data that you're processing, is it like inside the instruction, or do you have to separately go to memory to read data out from?
So it follows the same exact path as if you were any other instruction where it's being partially decoded and then it's sending. Oh, so you're the data, where the data is coming from. Oh, so that's what I was saying on the one that I lost all that stuff. It has its own vector register files within our vector coprocessor. It's not, oh, here we go. So they're shared, like level 2 cache, shared. But then the actual vector register files are within ARA, not within CVA6. It's lost here, but oh, it's really lost. It was on this slide. But what this arrow should be pointing to is external memory. And the load store unit will take that data, take elements of, I'm pointing at this screen, you can't see what I'm pointing at. We'll take data, load it into here, and then it will be distributed along the vector register files. So between them, because each lane has a chunk of the vector register files. They're distributed like, if you have 2 lanes, it would be like 0, 1, 2, 3, 4, 5. So your question is, where's this data coming from, right? Yeah, so that's where it's coming from. The data is coming, or either it's already in the vector register files that's in ARA, or it's coming from external memory and being brought in by, because ARA does have its own load store unit. It's being brought in and then distributed, and if needed, shuffled.
Does that mean, does ARA then get bottlenecked by its the main?
Oh, so there's a whole, I can link you to someone's done like 10 slides on that alone, where because of course there's like cache coherency issues, because a lot of them are accessing the same data, right, within the level 2 cache. So sometimes it has to like stop one, there's like write through policies. So it can cause issues, but they do have some workarounds. I can link you to something that will tell you all of them. I couldn't tell you off the top of my head.
I think that you should bring all that down so we can understand what's the
What the diagram is that we lost. I'll see if it works. Come here. You guys can look at my cute laptop. Look at this thing.
So HDMI is okay. The VLC.
Okay, it might take me a minute to. Okay, wait.
Sure.
Cute, right? Yeah. Okay, let's see the slide we lost real fast. You know what, let me go to the other one. Or maybe lab version is better. Wait. Okay, we lost. Oh, so none of this was in my slide today. This is everyone who was in my lab had to listen to me talk this morning too. Let me make that bigger. Okay. So this is kind of what it looks like more up close, right? So we've got an XBAR interconnect. This right here would just be a single lane. This is what is contained inside a single lane. So we've got SRAM banks, that's our vector register file. We've got each one has its own floating point unit and ALU, and then they're all interconnected to our shared units, which is our slide unit, our mask unit, and our load and store. That's actually pretty expensive because all of them are connected, so it's shared. And then what you were talking about was this little picture that we lost right here. Oh, no, back one. That we lost right here. Wait, sorry, your question is, say it one more time, apart from the memory stuff.
I'm thinking.
Or I can get up.
Something very important here is basically
Cache coherency.
your artificial intelligence running right? And I need to get it to play well with the CPU. If one way of doing it is I have an NPU and a CPU, and then I have this like interconnection. I write instructions like shared memory and the NPU separately to like a DNA or something reads those instructions in that memory, and they have that kind of mode of operation. Versus here, you've got like a coprocessor, which I don't know if that makes it like a different thing, but like I'm using my main CPU to decode my instructions, and then when it's a relevant instruction, I'm telling my coprocessor, and then that's separately going to read from memory the data that's being processed, and then it's processing.
I know what you're asking. So, yeah, well, the question I have for you is, are these things dependent on each other? So if I was to remove, if I had CVA6 just connected to the AXI and then another CVA6, and I remove one of them, it doesn't impact the other, right? But if I have CVA6 and ARA, and I remove CVA6, ARA doesn't work anymore. So that interconnection, it's not using that big bus, right? You probably could, you would take a lot of configuration, but the reason that they're connected like that is because it's kind of like an extension on top of the processor, right? It's dependent on it. It can't be on its own. It requires information from CVA6.
Yeah, so what I'm saying is how much of a speed up or efficiency benefit do I get by doing it in that way through the vector extension versus not
Scalar?
like versus not having vector extension, have like just sending commands to completely separate. You see what I'm saying?
I mean, I don't have the data on that. Is that a speed up difference? I mean, I would say test it, right? I'm not super versed in it because I'm only versed really in vector processors and regular processors and peripherals and like UARTs and stuff. So it's not something I could tell you.
Run floating point operations, I'm assuming.
Vector instructions.
Vector instructions.
Yeah.
But that I'm just doing a lot of floating point operations.
Yeah, so what we're trying to do is we're trying to make it so that we're trying to make the vector instructions do more, right? So our only goal is can we speed this up? Can we reduce redundant power? So instead of, if we can reduce the amount of times we have to actually run an instruction, or we can fit more data in the same amount of space, then we're reducing cache misses. We're increasing our throughput. I know what you're asking. I don't think it's 100% what I'm doing. What I'm doing is more to help people then when they're running their data and they're testing this. We want it to be faster. We want the power consumption to be lower. We want the area to be lower if possible. What's the difference between doing this and having a separate unit? Does anyone have any ideas? because I'm only versed on vector coprocessors and how they can be helpful. Yeah, please.
Yeah, I think it depends on your workload. So if your workload requires a mix of scalar and vector instructions, then I guess a vector coprocessor is having benefits, and it can run independently on NPU and don't need any kind of interaction with scalar. Then you can do it in NPU. And if your workload, yeah, I think it depends on your workload.
Yeah, what he was just saying, that's what here in our, when we're looking at both of them, I really don't need this, I'm too loud. When we're looking at both of them together, and I was saying that as far as CVA6 is concerned, the instruction is done. Even when it's not done, that means you can continue to use run instructions. And this can be scaled up. So it doesn't just have to be one scalar core with maybe you decide you want, all 16 lanes. So maybe you're just focusing really heavily on vector, but you don't care that much about scalar. Or you can balance it out more. You could have a ton of cores with Aura, but Aura could just have one lane. So you could, if you have like a pretty even split. That was fantastic. Thank you. So yeah, this end I can help you. That end, luckily, he's here. Any other questions, comments, concerns? Yes, hello. Please don't make it hard. Global control and status register.
So is there any risk in this proposal? Because maybe I can follow
We found.
maybe could be right by some in the model or maybe.
Safety-wise, we have not looked into the safety side. I'm gonna be honest, because when we were working with, actually that's one of the reasons we're changing some things with the vector, but on the scalar side, it was purely to see, will this work conceptually? On the vector side, one thing we're actually talking about just this morning is the fact that there's two reasons we're considering moving away from the scalar approach of modifying the V-type CSR. One is the fact that it still requires additional instructions, right? You still need those CSR write instructions. So that's one of the issues with that. But also, my professor was talking about having separate registers, something like that, so that we're not modifying something that is very crucial within CVA6, especially because those reserved bits, some people may want to use them for like long int. We're not going to do that, but so it is something we will look into if we decide to stick with the vector approach. Is how safe is that? Is there security risks? It's not 100% our like area of research, but it is something that I should think about. But good question. So if you're talking about the, I'm going to have to send you over to our compiler people. Oh, that's not that one anymore. So if you want performance information, I'll send you to our compiler team because I have some, not on the vector side, on the scalar side. They did run testing. Mine's just verilator to make sure everything works. But if you want information on results and stuff like that, I can link you over to our compiler team. I'm the hardware person, so I can explain basic things here. But for the most part, if you want details on what exactly they were running and what they were testing with, this was just a very brief thing. I can also link you to a little paper and everything, but I might have to pass you on to our compiler. We have one here today. I don't know if he's still here, but yes. So probably is data, but I don't have it. Of course. We've got one more in the back. I can go get him.
So can your Aura coprocessor accept data from the CVX6 or response back data?
So it doesn't take. I'm gonna steal it back.
Sorry.
I apologize. It doesn't. So CVA. So Aura does not get data. So it doesn't take from the data cache of CVA6. It has shared memory, but R itself has its own vector register files.
So can Golang execute some instructions that need both scalar and vector register? Or this is more focused on your like deploying?
So at the moment, what we're focusing on is floating point, but at the moment, what we're focusing on is vector-vector operations. In the future, we will look into, I mean, there's so many to look at, right? In the future, sorry, the camera. In the future, we can look into things like that, but at the moment, one of the biggest things is getting things like microscaling formats actually working, especially for something like floating point 4. It's kind of our priority, so we're sticking with vector to vector for the moment. All of that is future. We also, at some point, would like to make custom instructions, like to do decision trees and stuff. But at the moment, we're not touching that. But in the future, if I can get everything to work, of course. And if you have suggestions, anything like that, please.
So it cannot compare with like the last question that if there's one core that's supporting vectors and extension, then in this case your SOC would not support vector extension.
This?
Yeah.
This supports vector. It's R as vector.
No, I mean, because you're missing some instructions. So.
Oh, so there are already instructions. I'm talking about the instructions that we're working on. It does support other instructions as well, but for what we're working on for sub-floating point 8 right now is vector to vector. It does support other instructions. They're just not ones that I've touched.
Oh.
I can also show you if you want to look later on my computer. Any other questions? Okay, in that case, if anyone wants to look at it or look at any of the code, or I'll run this up in Vivado, they can come down and look at my tiny computer. It's wonderful. Great. Thank you for listening.
直播同步间的伙伴，我们在 EC122的主教室即将进行大合照，希望入境的朋友们也欢迎回到 EC122回来。
先帮我往中间做 ，OK， 我问你的照片啊，同学，哦，哎，同学。好，大家都准备好了吗？等一下，地头送。手机。哎，那个红色衣服的同学，你要再进来一点。OK， 看我，1、2、3，好，我们比个爱心。那个脸颊爱心。好，脸颊爱心哦，1、2。 好，谢谢大家。
Everyone else can see something from paper that on the domain. You just simplify the code. Oh, okay. What is it?
哎，千万不想拍照。